This conference will now be recorded.
So very good evening, students. Today we are starting revision on the chapter ray optics. So here basically we'll see these properties like problems which are being asked in previous years. Properties we will look for both plane mirror and also for the curved surfaces like spherical mirrors, etc. Okay, so we have picked up few questions today from previous year's JEE papers. So I have started picking up questions from 2000, year 2000. So the first question you can see here, a rectangular glass slab ABCD of refractive index N1 is immersed in a water of refractive index N2, where refractive index of the glass is greater. We know that glass has N1 refractive index in this case. So N1, if we require some time, we can get this N1 for refractive index. Refractive index for glass is this normal glass, and N2 for water it is 1.33. We know very well, so that's why N1 is greater than N2. That means if a ray goes from the glass to water, it will go from denser medium to rarer medium. So that is what is the point. So a ray of light is incident at the surface AB, of the slab as shown in the figure. The maximum value of angle of incidence. So this is called angle of incidence, and see the maximum value of angle of incidence such that the ray comes out of the other surface from the other surface CD. So you look, this is a question from actually waveguide. This is the principle for waveguide or optical fibers. Okay, waveguide. So wave actually is guided through these optical fibers to come out from. See, if you guide the, like if you have waveguide or optical fiber, you have optical signal from here. It is, suppose it is entering. This is actually flat portion seen shown here for simplicity, but you know you have kind of tube, okay, cylindrical symmetry, and you have, see the cross section of this. See here actually there should be, this is the same, actually same principle here. It is called as glass slab spine, but this is the same, this has the same principle of total internal reflection of the waveguide. So what happens in waveguide or optical fibers, if you choose a certain angle of incidence and maximum angle, see maximum angle of incidence at this surface, okay, or the interface of this N2 and N1, that means water and glass, such that this ray suffers total internal reflection at here AD, and then get reflected back such that it comes out like this. Okay, so there should be total internal reflection obviously here, otherwise it is not possible to come out of this CD and CD of the slab. Okay, so there should be total internal reflection. Let us just see the schematic. See, if this is the incident ray, after slight refraction happens here, it goes here, and at this interface this has actually N2 and this side is N1. That means the ray is going somewhat towards from the glass to water. That means there is travel of water, sorry, ray of light from denser medium to rarer medium. So at this case, if this angle of incidence is becoming theta c, then there will be total internal reflection. Okay, and then only this ray, after entering here, it will be able to come out through this face. Okay, CD. All right, let us do one thing. Let us okay, so we have to find out the maximum angle of incidence such that the ray comes out from the other side, other surface CD is okay. So that can be written as this. Okay, for the ray which comes out through CD, the angle of incidence, sorry, maximum angle, this angle of incidence, maximum angle of incidence will be such that the ray comes out through CD phase. Okay, so for that, let us say this is a refraction angle of refraction at this interface, the first one, and this is refractive index, angle of incidence at this surface. Okay, and you look, this is again, since this is perpendicular to the AD and this is perpendicular to AB, so this must be 90 degree. So if this is the case, you know, you will get 90 degree. R1 plus R2 is equal to 90 degree. So now if we find out what is R2 or what is R1, because we need to find out. So let us say what is R1, that depends on actually this R2, value of R2 also. See, if my alpha max, this becomes max, this also will become max. So see, R1 has to be max, so this has to be max. Okay, if this is becoming maximum, then this R2 must be minimum. Okay, R2 must be minimum. Let us say this R2 minimum, let us say, okay, we have got R1 to be maximized, R1 to be maximized, 90 minus R2. R2 has to be minimum. Okay, now this R2 minimum, let us take this as theta c. Theta c, then what happens? R1 max. R1 max is equal to 90 degree minus R2 that I am writing as theta c. So I am writing here as theta c. Okay, this is the theta c. Now look what we will do. We'll actually apply Snell's law at this particular surface. Snell's law for this particular surface. So if we now find out, see, at this interface, if we apply, so this is, then let me write N2, N1 sine R1, R2. So this is in general. Okay, so this is the angle of incidence R1 and angle of refraction is R2. If that is the case, okay, so it will be sine R1, and this into sine, so this should be sine theta c. Okay, at sine theta c again, if this is sine theta c, then we'll see we have to actually reach up to the angle of alpha. Okay, so sine r1 is how much? Sine r1 means here this, and that can be replaced by this. So sine r1 is actually, see here n2 is this, what I have to write n1 actually according to the figure, n1, and here it is just a minute. So we are just writing Snell's law at the interface, this sine r1 n1 sine. Okay, fine, this is okay. So we'll just rub it once. Let me write down what we have got. This minimum, okay, or this is theta c. Okay, so now at the exactly at theta c, what will happen? N1 sine theta c is equal to n2 sine 90 degree. Okay, this is the case. Then you know sine theta c will be n2 by n1. Okay, so this also we get, and now if we just apply at this interface, then n2 sine alpha max sine r1, this has to be max, and see we have got r1 is equal to, okay, so this we have got as 90 degree minus theta c itself. So we'll just put it here, n2 is fine, so sine max, let me write sine alpha max n1 by n2 into sine r1, sine r1 means 90 degree minus theta c. Okay, now we have got sine theta c is this. Okay, so n2 by n1 we can actually write sine theta c, sorry, 1 over sine theta c, and this to be sine, in fact we can write that as cos theta c. Okay, so we have got here up to here, what we have got is, look, I'll write here itself. So I am making use of this into this. Okay, let's say this is equation number 1. Now we are putting this value to equation number, this equation, okay, this particular equation. So n1 by n2 I am just writing as 1 over sin theta c, and this is cos theta c. Okay, so what we can write now is that Okay, okay. So in the options there is no cot theta c and all. Rather there is n1 over n2, n2 over n1 like that. So let this be n1 by n2 itself. Okay. So then you know what you get, sine alpha max is equal to n1 by n2, then cos theta c will be square root of 1 over sine square theta c. Okay, again sine square theta c, or let me just see, look the option here, cos of sine inverse of this. Let us keep like this itself, so no need to go for again n1 into, see n1 by n2 we have here. So cos theta c, so this will be cos of theta c means again sine inverse n2 by n1. Okay, so n1 by this, so we have got this as sine alpha max. Okay, let us just summarize it here what we have got. So sine of alpha max, sine of alpha max is equal to n1 by n2 cos of sine inverse n2 by n1. Okay, so look here that alpha max will be sine inverse cos, sorry, this here it is sine inverse n2 by n1. Okay, so this is how we can see. It may be a little bit hazy here. I'll just write the answer now. See, the answer will be, okay, so alpha max will be sine inverse of n1 by n2 sine inverse n2 by n1. Okay, so these are the things we have got. Actually, this is the answer. Okay, so we'll go to the next question. So this question is also from 2002, and it is really very interesting problem. So what does this say? Which of the following spherical lenses does not exhibit dispersion? The radii of curvature of the surfaces of the lenses are given in the diagram. So to solve this problem, you have to be very much judicious, and you have to actually have some idea about dispersion at the spherical surface. So now we'll analyze which of the following spherical lenses does not exhibit dispersion. So that is the question. So how do you solve it? we'll see how dispersion is related to refraction, or this dispersion related to the radius of curvature, nature of the curvature, how it depends on like how are how are these factors affecting the dispersion. Okay, we know what is dispersion. Dispersion means, like if you have a prism, okay, if you have a composite light, white light, after refraction at these surfaces, actually there may be many colors. Okay, there may be many colors. At least in in white light there are 7 colors, major colors. So when light with different wavelength passes or refracts through a prism, each of them has different velocity while passing through the prism or material of the prism, and that's why some of them will take greater time and some of the component of the lights will take lesser time to cross over that particular thickness of the prism. So that's how some light gets bent, almost like all the light gets bent, and some of them gets bent too much. Okay, so anyway, so dispersion means the splitting of the light into its component colors. So that is actually dispersion, and that depends on refractive index of the material, the color or wavelength of the light. Not only that, if we have other than prism, if we have some other curvatures, so this dispersion, angle of dispersion depends on the radius of curvature and nature of the radius of curvature. Okay, and this if we write down the formula for the, see, if we have two curved surfaces having different radii of curvature, so this will act as actually a lens, suppose. Okay, then what will be the focal length of this particular system? So focal length can be actually found out using this 1 by f. Okay, 1 by f. Then if it is between this medium and air, this is refractiveness mu, this is air, so we get mu minus of 1. Okay, so this is approximately, yes, this is the actually expression for the focal length. You might be surprised, why do we need this focal length with radius of curvature, etc. See, this depends actually. See, if somewhat, like if the focal length is greater, then bending will be actually more. If the focal length is less, then bending will be less. Bending will be less. Okay. If the focal length is more, then bending will be less. If the focal length is here somewhere, bending is less. But if this is here, so bending is more. So anyway, if we find out, if we find out some non-zero value of this after taking derivative with respect to distance, okay, so this should be 0 for no dispersion. No dispersion system. For no dispersion to occur by the system, this derivative of the focal length, that should be 0. That means what? R1 must be equal to R2. Okay, so when there will be no dispersion, so this is the condition. Okay, so in these, you look, this is plano-convex, so this has infinite radius, this is having r. This is infinite, this has some like line, so the which is, this is actually called plano-concave and this is called plano-convex. So this, even this actually double convex, sorry, double convex, and this is also double convex. So plano-convex lens, they have actually one radii at infinity. So plano means this plane surface at focal length or radius of curvature infinity. And so that means actually, see the dispersion or angle of refraction introduced here and here must be having a huge difference. Okay, so no dispersion to occur. This radius, so this option will be the correct. Okay. All right. See here in this case, you know what will happen? The cancel out to cancel out the dispersion effect. See, these two have same radius of curvature, so the bending of any ray, any color will be the same. Not only that, the dispersion will be in some okay, so the dispersion will be same in amount and the direction of the dispersion also has to be opposite to each other. So that's how it will not produce any dispersion. Okay, we'll go to the next problem. So this is another problem which was being asked in IIT JEE 2003. So this question is again related to the total internal reflection. So we can just apply Snell's law and try to solve this problem also. Let us read the question itself. The question is, a ray of light is incident at the water glass interface. Okay, at an angle of incidence I. Okay, the angle of incidence is I. Now it merges. Okay, so this is actually this okay, this merges, it merges finally parallel to the surface of the water. Look this, so this is glass, this is water, so at the interface light is incident at an angle I, and see finally when the light is coming out from glass to water, water to air, so the ray has become actually parallel to the water surface. Now you have to find out, so mu g is actually the glass refractive index of glass. Okay, so here then the value of mu g, okay, you have to find out what is the mu g. You have to find out mu g. Let us say mu g is refractive index of glass. Okay, mu g, refractive index, I'll write in short, refractive index of glass, refractive index, refractive index of water. Okay. Now basically these are actually mu g. This means a mu g. That means it is with respect to air. Similarly, mu w, I mean to say a mu w. Okay. Now the question is, what is mu g? How to find out? We'll just do one thing. We'll just write Snell's law at these two interfaces. Let us see what we get here. So refractive index, see here we can write. So this is suppose mu g, this is mu water, and this is again mu air. Okay, so we can just write here mu g sine I is equal to mu w sine r. Okay, this is fine. Now look here. Here also we will write mu w sine r is equal to mu air. It is coming out mu air with sine 90 degree, because when the imaginary angle grazing the surface of the water, so this is the thing we have to write. So what we have get, so mu air is 1 and this is actually 90 degree, that is also 1. So we have got mu w to be 1 over sine theta. Mu w, we have got mu w, but we have to find out mu g. So look this, we know that we know that here mu w a mu w is equal to 4 by 3, we know. Okay, so if we want to write w mu a, you have to write, just take the reciprocal. So 3 by 4. So if we write w a, mu w a, just we have to take this, means you know you have to take reciprocal of this. Okay, so we have got this too. We can write now, see we want to find out refractive index of glass. Mu g means a mu g, we have to find out a mu g. So let us say a mu g divided by a mu g has to be written like this. Okay, so mu w mu g, all right, fine. Mu w, we already know that this is 1 by sine I sine r, this is sine r, theta means sine r over here. Oh sorry, so here it is 90 degree, here it is sine r, this is sine r. So sine r we have to find out from here. Mu g sin I here mu w sin r. Okay, so we have already got what is mu w. We have got mu w to be 1 over sin r. Okay, so this get cancelled from each other. This get 1. So mu g will be actually 1 over sin I. So this is actually the answer. Okay, so this is the answer. Mu g is equal to 1 over sin I. This is the answer. Okay, so we'll take up this question again. This is a point object is placed. A point object is placed at the center of a glass sphere. Okay, a point object is placed at the center of a glass sphere of radius capital R. Okay, now this R, radius R is 6 and refractive index of the glass is given mu g, as you know, a mu g, this is 1.5. So what is the distance of virtual image from the surface? So here, look, we'll try to depict here. See, a point object is placed at the center. Let us say this is the center. Center of glass sphere. This is a glass sphere. Glass sphere. It has radius. See, radius is 6 centimeter. Okay, this from here to here, and also from here to here. This is refractive index. Sorry, the radius of curvature. Okay, now the distance of the virtual image. See, you know this when this is a complete sphere, glass sphere. It has two curved surfaces. You look, this one surface is this one. See, this is air. This is glass. So if the light comes from this, so this is the point object, and hit here. So there are two possibilities. One is reflection, another one is refraction. So suppose this gets refracted. Okay, so now the question is, what is the position of the virtual image? Look, this distance, if I say this is the object, if I just take this as, so this side as part of the lens, spherical lens. If I take this right hand side, this will be this will act as a spherical lens, and there will be reflected rays and etc., and there will be an image formed. Okay, that image, if somehow is formed here or somewhere in front of this particular surface, then that object will actually get reflected by this also. Okay, so that's how. Look, if I just write, at least for this particular surface, see, so this is glass, say this is mu2, this is air, mu1. Now look, given u, So this U is and say this R radius of curvature. This radius of curvature is also here minus R. Okay, you might be thinking why. If I say this is R1, this R1 is related to this. So from here, if I'm just thinking that my point object is here, okay, so R1 is fine. Now if we write the formula at the curved surface, see how we can write, for refraction we write mu2 or n2, whatever, mu2 by v minus mu1 by u. Then we write mu2 minus mu1 by r. Okay, now look, if we just put the values of this r, then u and v, so from here some refractive indices we know. Therefore if we just put the values, see mu2 v and u, so this is image distance, this is object distance. So mu2 by v, this is fine, all right. This is 1 by nu 1 by v is equal to, as you know, I'm just writing this for the right hand surface. So you know this is mu2, this is mu1. So according to our this thing, we can write 1 over v is minus 3 by 2 r. 3 by 2 r, because mu1 is for the glass is 1.5, so 3 by 2. This mu2 is the air. Okay, this is the air and this is the glass. So that's why this mu1 is 3 by 2 and u is again minus r, so that's why this comes here. This is equal to 1 by 2 capital R, right? So look from here, if you solve, we get this to be 6 centimeter. Okay, I hope you have understood this. This is the master formula for refraction at the interfaces. Okay, where you look, if there are like curved surface, I'm just recapping a little bit about the theory. If you have this kind of interfaces, curved surface, so you have here mu2, sorry, mu1 and u1 object distance here, and then you have mu2 refractive index and the distance of the image will be v, right? So this is how this is written here. Now again, so r can be written with proper sign. Okay, so here we have put mu2 is equal to 1 because refractive index here, I'm sorry, this you have to take as mu1, here it is mu2. So mu2 is air here, so refractive index 1. Then r, so this has to be taken from here. Okay, so mu1 is again Okay, so this is how we have actually uh, written down here, and last two steps are much important. Okay, so this is how we get to see that the virtual object will actually be produced 6 centimeter from the surface, and it is actually this image will be actually virtual image. Okay, that's how. Okay, so this is the answer here. So we'll stop it here for today. We'll pick up many more problems on this ray optics part. In fact, ray optics ray optics seems to be a little bit tricky since geometry and all those things are involved. We'll slowly take up various problems, various typical problems, which are asked in in the last year's JEE papers, like including main and advanced questions, and we'll solve in the subsequent classes. So thank you for your patience. Bye for today.